Good morning, everybody. This is April the 10th. It's Math 0310. A couple of announcements before we get started. WebAssign homework. You have two sections that are due on April the 15th. That's this Sunday. So you have an assignment on sections 4.4 and 4.5. That's just one assignment. That's due April 15th. And the assignment on section 4.6 is also due on April 15th. And then April 24th, you'll have 4.7 and 3.5 from the intermediate textbook is due also. And I'll explain a little bit about that and again in a second. So let me erase that word there and make it actually the word text. There we go. Exam 3 is the review is posted. I did post the review yesterday. So that is on your Google site, remember? And that is a very, very good review of everything that you are going to need to know for Exam 3. It's lengthy, lots of problems on it. That gives you lots of practice problems. But please start looking over that review and start working on it going into this weekend. The window for Exam 3 is April 19th through the 24th. Office hours, let me remind you of my office hours. I have online office hours Tuesday, Wednesday, and Thursday from 11 to noon. And Sunday and Tuesday from 8:30 to 9:30 p.m. So don't hesitate to come by my online office for questions. I'd be happy to help you out during those times. I will be on campus next week, April 18th and 19th. 18th from 4 to 6, and the 19th probably 9:30 to 11:30. But don't hesitate to come by my office in person if you have some questions going into Exam 3. I'd be happy to help you out. Today, we will be covering section 4.7 on linear inequalities. We've been talking about linear equations in two variables, and so now we're going to go on to linear inequalities in two variables. And then after we finish that, which really won't take us that long to get through, then we will be starting in on Chapter 3 material from the intermediate algebra textbook. So let me point out that throughout the semester, we have been using the OpenStax elementary algebra textbook, except for a couple of sections. There's 3 sections that I've added from the intermediate algebra textbook. And so today we will start in on material from the intermediate algebra textbook. I have taken those 2 sections out of the intermediate algebra text and have actually put those as a file on your Google site in syllabi and other documents. So if you're looking for sections 3.5 and 3.6, you don't have to go and download the intermediate algebra textbook. You can just go to my Google site or go to syllabi and other documents, and those 2 sections are sitting there. And you can bring those up, and there's good practice problems out of those 2 sections that you can use to help you prepare for both the Exam 3 and for the final exam. All right, so those are some quick announcements, and so we are going to go ahead and get started. So let's see. We are talking about linear inequalities in two variables. So far, we've been talking about linear equations in two variables. So emphasis on the word equation there. Linear equations in two variables. And we know the graphs on those are lines, right? The graphs are lines. So we've done a lot of work with that over the last couple days in class. So as an example, if you have y equals 2x minus 1, and you're just graphing that line, a couple of different ways you could graph it. One way is to plot some points. Another way is you could use the fact that it's in slope-intercept form, right? You know that the slope of this line is 2, and you know that the y-intercept is at 0, -1. So that gives you enough information right there to make a quick, decent sketch of the graph, right? You know that the graph goes through 0, -1, and has a slope of 2. So it means you go rise is 2 and the run is 1. So you go up 2 and you go over 1, up 2 and over 1, and you could do that forever, right? And you get points, additional points on this line. And so here's our line right here. And remember, we're saying that every point on that line, every point on this line is the solution to that equation in 2 variables, right? And so we say that that graph is the graph of the solution set. That graph is the graph of that equation. All right, now what we're going to do today is we're going to look at linear inequalities. So emphasis on the word inequality in 2 variables, and how you look at the solution set for something like that. So we are talking about possibly an example like this. Instead of y equals 2x minus 1, this is y greater than or equal to 2x minus 1. Right? So with an equation, you've got the word or the equal sign there. With an inequality, you've got what we call an order symbol. And one example of an order symbol is greater than or equal to. You know, and remember that there's other examples like that. That's not the only order symbol that we have. So other examples would be, you know, y, whoops, let's make that look a little neater here. Y greater than 2x minus 1, y less than or equal to 2x minus 1, y less than 2x minus 1. Right, those are all examples of linear inequalities, right? And so notice that instead of an equal sign, we have one of those order symbols in there. And so we'll look at this as our first example, y greater than or equal to 2x minus 1. Now, what happens is the solution set to an inequality like this is different than the solution set to an equation. If you graph y equals 2x minus 1, which is a line, right, just like we saw at the very top of the screen, this serves as the boundary or the edge, so you could say the word edge there, of the solution set to this inequality. All the solutions to the inequality lie on one side of the boundary. Okay, so this is what I'm talking about. Let's see what that means there. It says the line, if you take the inequality y greater than or equal to 2x minus 1, and you replace the order symbol with an equal sign, right, you get a line, just like we got at the top, and that line is the boundary or the edge of the solution set. All the solutions to the inequality are on one side of that line that you graph. And so it's literally the boundary for the solution set. All right, so what do? We graph, just like we did at the top, we graph y equals 2x minus 1. So it's the same graph I got at the top of the screen there. Right, we've got these points that we plotted like that. And so that is the edge of the solution set. And so all of the solutions to this inequality are either above this line or they're below this line, depending on the inequality. And that's what we have to do, is we have to decide which one it is. So when I say it's either above or below, what that means is that the solution set, now I'm going to make little tiny graphs here. In fact, let me make a little bit more room here for us. I'm going to erase a little bit of that line, and I'm going to take this graph and I'm going to kind of slide it over here like this. All right. So what I'm saying is that the solution set to this inequality looks something like this. And I'm going to do just little rough sketches here off to the side. Here's our boundary line. Looks like that. Either the solution set is all of the points above the line. In other words, you would shade, literally shade above the line like this, or you get the same line, the same boundary, the same edge there, and the solution set looks like this. Here's our line, and it's everything below the line like this. It's one of those two. And the question is, which one is it, right? Which one of those shadings describes the solution set for this particular inequality? And so the way I do that, the way I check that, is I actually just test a point. And what I do is I test 0, 0 in the inequality. And I'm going to write the little test up above here, make a little green box here, kind of separate it from everything else. And so I'm going to literally test a point, and I usually test the point 0, 0, which is the origin. And I literally test it in the inequality. When I say test it, I'm literally just plugging in 0 for x and 0 for y. And then I see what I have when I do that. I get 0 greater than or equal to -1 when I do that, because 2 times 0 is 0. And so 0 greater than or equal to -1, the question is that true or false? True or false? And the answer here is, don't think about this, don't make a careless mistake, but 0 is bigger than -1, right? 0 is to the right of -1 on the number line. And so this is true. And so what do we have here? We have that 0, 0, that point right there made the inequality true. It was a solution to the inequality. Now look at the two possibilities off to the right here. Here's where 0, 0 was, the green dot. And remember, the shading is supposed to shade the solutions. So which one of those pictures makes sense in this problem? Remember, the green dot is a solution in this particular inequality. And so since it is a solution, it would have to be the shading on the top. The first one that I did right there would have to describe the solution set here. And so the solution set to this inequality is all of these points above the line. If I take any of those points, no matter where they are, and I substitute them into the inequality, it's going to make it a true statement. If I take any points on the other side of that line and I substitute them into the inequality, it's going to guarantee to make it a false statement. And let's go ahead and check that. Let me show you what I'm talking about. Like if we pick this point right here, that is the point 2, -1. And when you take the inequality y greater than or equal to 2x minus 1, and you put -1 in for y, and you put 2 in for x, you get -1 greater than or equal to 4 minus 1, or -1 greater than or equal to 3. And that is false, right? So that means that point's not a solution. And notice it makes sense. Notice we didn't shade that point. We didn't shade that side of the line. So all of the solutions to this inequality are above this line, and so that's why we shade it. Also notice that the line is solid and the reason why the line is solid here is because we've got a greater than or equal to, like that. The equal to means that if y equals 2x minus 1, it is the solution. And so that means the line is actually part of the solution set. If it had just said greater than, then it would have been a dashed line, right? So we would have made the line dashed, or dotted if you want to do it that way, dashed, if it had just said greater than. Right? Greater than would have meant that you don't want the statement to be true if you get an equals there. If you get the same quantity on both sides, you don't want those to be solutions. And so that would, you get a dashed line if it says greater than, you get a solid line if it says greater than or equal to. All right, so there's our first example of a linear inequality. And so let's go ahead and walk through the steps again on a couple of more examples. And again, for those of you who are with me live today, please shout out if you have a question about something as we go through this. All right, so the next problem is 2x minus 3y is greater than 6. 2x minus 3y is greater than 6. All right, so first of all, what do? We graph the boundary. I'm going to write the word boundary, and remember, boundary means the same thing as edge here. The boundary or the edge of the solution set is the equation 2x minus 3y equals 6. All you do is take the order symbol and you replace it with an equal sign, and that is the boundary. Now, with 2x minus 3y equals 6, the way that particular equation is written, it's probably easiest to graph this by just using intercepts. You know, make a little t-table here, and you've got the x-intercept, and you've got the y-intercept. Remember, the x-intercept 0 is in place of y, and for the y-intercept, 0 is in place of x. So when 0 is in place of y, you just get 2x equals 6 or x equals 3. And so you have an x-intercept at 3, 0. And when at 0 is in place of x, you get negative 3y equals 6 or y equals negative 2. So the y-intercept's at 0, negative 2. And so we've got the boundary to go through those 2 points, 3, 0, and 0, negative 2. Now, when I do this, because this is strictly greater than, that's the inequality we're graphing, I am going to make this a dashed line, right? Because this says greater than, we're going to make the line a dashed line. That means the line is not part of the solution set. Line is not part of the solution set. All right, so we go ahead and make this dashed line like so, and that is the edge of the solution set to this inequality. All right, so to decide which side we're going to shade, so remember what we're going to do is we're going to shade one side of that line. So to decide which side we shade, we're going to pick a test point. And I typically would pick 0, 0 as my test point. The only time you can't pick 0, 0 is if 0, 0 is actually on the line. And we'll look at an example of that next. You can pick any point you want as a test point. It does not matter. It just can't be on the line itself. I pick 0, 0 because it makes the arithmetic easy. So we test 0, 0 in the inequality. You have 2 times 0 minus 3 times 0 greater than 6. So that's just 0 greater than 6. And that statement is false, definitely. Right? That is definitely false. So 0, 0, that point right there is does not make the inequality true. It makes it false. It's not a solution. So where do all the solutions have to be in this particular graph then? Well, above the line, that's false. So below the line, it's got to make it true. If you are worried about that, then pick a point that's below the line. If you are really nervous about this. Now, you don't need to do this because I have enough information to know it's the other side. But if you get nervous, then do that. Take a point on the other side of the line. Like, let's say I might pick this point right here. That's 3, negative 2. So we're going to test 3, negative 2. So this is 2 times 3 minus 3 times negative 2 greater than 6. So you get 6 plus 6 greater than 6. And you get 12 greater than 6. And notice that makes the inequality true. So that point is a solution, right? 3, negative 2 is a solution. 0, 0 is not a solution. Very clear cut here. Where are the solutions to this inequality? They have to be below the line. Notice that the inequality was a greater than, but I was shading here below the line. So it depends on how the inequality is written as to which side you're going to shade. And so don't depend on the inequality itself to just tell you which side of the line to shade. But notice in this case it said greater than, but I'm still shading below the line. And all of those points are solutions to this inequality. All right, so let's look at another problem. Let's say we have x minus 3y is less than or equal to 6. X minus 3y, whoa, I'm sorry. That's not what I wanted to do. X minus 3y is less than or equal to 0. There you go. That's what I wanted. All right, so the boundary for this inequality is the line x minus 3y equals 0. All right, and if you notice that if you try to use intercepts here, when you put 0 in for x or for y, you just get 0, 0. And unfortunately then, this line goes through the origin, so you need another point. Now what we have done in class before, when you need another point, is I've solved the equation for y, so I subtract x from both sides, and then divide by negative 3. You have a negative divided by a negative, so that's a positive. So you get y equals 1/3 x. And so that means that when you substitute x equals 3, you get y equals 1. You get the 0.31. All right, so I needed that extra point in order to graph the line, the boundary to the solution set. All right, so let's see what we've got for the line here. We've got the line going through the origin, and we've got it going through 3, 1. And because this is greater than or equal to, this is going to be a solid line. And so here's our solid line like this. That is the boundary to the solution set here. And now notice you can't pick 0, 0. So 0, 0 cannot be a test point. So let me write that. 0, 0 is on the line, so cannot be a test point. So I pick something else, so just something that's not on the line. It doesn't matter what point you pick at all. So if I pick this point right here, I'll pick 0, 2. So 0, 2 I use in my inequality. So my inequality is x minus 3y less than or equal to 0. So that's 0 minus 3 times 2 less than or equal to 0. And that gives you negative 6 less than or equal to 0. And negative 6 is less than or equal to 0. That is a true statement. So 0, 2 is a solution to this inequality. It made the inequality a true statement. And so in this problem, I am going to shade above the line because that's where 0, 2 is, right? I shade the solutions, and since 0, 2 is above the line, that's where I'm shading. Notice the line is solid. That means the line itself is a solution. Those points are also solutions to this inequality. And, you know, like I've been talking about, if you are worried about that, then certainly pick a point that is not on the that's on the other side of the line and make sure that that makes the inequality false. So like here's the point 4, 0. And if you tested 4, 0, you have x minus 3y less than or equal to 0. So you have 4 minus 3 times 0 less than or equal to 0. So that's 4 less than or equal to 0, which is false. Right? 4 is greater than 0. So that makes sense. That point should have made it false because that was on the unshaded side. All right, so I have maybe one more problem to do here, and then there's really not much else that we're going to talk about with linear inequalities. I just want you to be able to go through what the steps that I've been talking about. Okay, so let's say we have y greater than -3. Y greater than -3. Now don't panic. Don't do anything different because the x is missing out of this inequality. Don't do anything different. You write down the boundary at the beginning, and the boundary is the equation y equals -3. And what do you know about that kind of equation? Its graph, because it's y equals a constant, don't forget last week we talked about this a lot. This is a horizontal line. And so the graph of this equation, the graph of the boundary, is a horizontal line at y equals -3. All right, so also because it says greater than, this would be a dashed line. So you have a dashed horizontal line through 0, -3. That's the boundary like that. And now you've got y greater than -3. So like again, you could don't do anything different. Just pick 0, 0 as a test point. Here's 0, 0 right here. You're going to check 0, 0. That's our test point. And you put it into the inequality y greater than -3. Now there is no x here, so all you're doing is putting 0 in place of y. And 0 is greater than -3. It's true. And so that would tell you to graph above the line, or to shade above the line. And it makes sense here with y greater than -3 that you'd be shading above the line in a problem like this. Right? And so here is our solution set. All the points above that line, y greater than -3. So don't do anything different when you have a horizontal or a vertical line. All right, so that finishes our discussion on lines, basically, directly. So this finishes, let me say it this way, this finishes our discussion on lines, right, with this stuff with linear inequalities. And this is really about lines also because the lines are the boundaries to these solution sets. And so what we're going to do next is we're going to continue talking about graphing. So that's something we're not going to be leaving. We're still talking about equations in 2 variables. But now what we're going to do is we're going to turn our attention to the idea of a function. And so I'm going to write, that's what we're talking about now, is functions. And for the next couple of days, that's going to be exclusively our discussion. So when I say the next couple of days, the rest of class today, the rest of our lecture today, all of our lecture on Thursday of this week, and all of the lecture on next Tuesday it's all going to be about functions. And then we have our test. And then when we come back, we'll only, after the test, we'll only have 2 lectures afterwards, and we're going to turn our attention to inequalities and absolute value. And that's going to be kind of our last thing that we're going to discuss this semester. All right, now this idea of functions right here that we're going to deal with for the next couple of days is absolutely huge for those of you going on to college algebra. If you have some basic ideas about functions and some basic understanding of what a function is, function notation, how to deal with some very basic things about functions, I can't tell you how much stronger that's going to make you as a college algebra student. And so, so this is an important topic because college algebra is like a functions class, that the whole thing is about functions. And here we are, 3/4 of the way through the semester, and this is our first time to talk about the idea of a function. College algebra, we can talk about functions at the very beginning of the semester, pretty close to the very beginning, and the rest of the semester virtually is all going to be all about the idea of a function. All right, so what I'm going to do here is I'm going to state the definition for a function, and then we're going to pause because it's a lengthy definition, and then we're going to actually talk about what the heck the definition means and see if we can figure that out. So a function, remember we're still talking about ultimately equations in two variables. A function is a correspondence between two sets called the domain and range. All right, so first of all, it's a correspondence between two sets called the domain and the range. So a correspondence simply means a way of matching the elements up, a way of pairing the elements up. A rule that matches elements between the two sets. And these two sets have special names. They're called the domain and the range. All right. The correspondence, or this correspondence, must match every domain to a range. All right, so that's important. It has to match every domain element to a range element. And each domain can only be paired with exactly one range. Also important. Every domain is paired with only one range. All right, so, if you read through this definition, I can certainly understand where this might be confusing as to what exactly this is all talking about. And so, that's what we want to spend some time talking about and deciphering this definition. Now, I'm definitely going to leave a space underneath this definition because I want to write some things down that I'm going to come back to in a minute. So, like if you are taking notes, whether you're watching this recorded or whether you're watching it live, if you're taking notes and you've written down this definition, then leave a space underneath it because there's some comments we're going to write down afterwards that are important. So we are going to actually explore the idea of a function here by looking at some examples. And so what we're going to do is we're going to start off with the domain. And the domain will be the set of people in our class. All right, the set of people in our class. And that includes me, by the way, because I'm in the class too. So it includes Polito also. And the range is the set of, not set of people, set of makes of car, of automobile. All right, so the domain, we usually use the capital letter D. We could write out the domain. And so, for example, I'll use the people that are with me live today. So you have Gianna and Raina and Sandra and Shrell, and everybody else that we list. And that is our domain in this case. And then the range is the set of makes of automobile. So makes of automobile would be things like Ford, GM, Toyota, Honda, VW, things like that, right? Those are the makes of car. We can write out that list also. Now, we don't have enough to talk about a function yet. Now we must have a rule that actually pairs elements from the domain with elements in the range. So we must have a rule that pairs domains with ranges, that assigns domains to ranges, right, where domains correspond to a particular range. All right, and there's all sorts of rules that you can have between these two sets. Some of these rules satisfy the definition for a function, and so they're functions, and some of these rules do not satisfy the definition for a function. If it doesn't satisfy the definition, it's just called a relation or a relationship. Right, any old connection between a domain and a range is simply called a relation. A function is a special relation. So a relation is any pairing of domains with ranges. No conditions. So that's any pairing. A function is a special relation that satisfies the definition on the previous screen. And so that's what we want to do, is we want to look at some rules and decide whether we just have any old relation here, we just have a relation, or do we actually have a function. All right, so the rule 1 would go like this, that every domain, everyone is paired with the make of car in which they last arrived on campus. So the last time you went to campus, whether it was the North Harris campus or the Tomball campus or Montgomery or wherever you were on a LSC campus, the last time you did that, what was the make of car you were driving? Right, that's the rule. Okay, so let's see if I can talk to the people that are with me right now. So Gianna, I don't know. Hopefully you're still there, Gianna. What's the make of car? So I'm asking you, what's the make of car when you last arrived on campus? Gianna, are you there? So maybe she has stepped away. So we're going to make something up here. So we're going to say Ford for Gianna. Raina, are you there?
Yes.
All right, Raina, what's the car that you were in the last time you arrived on campus?
Toyota.
Okay. That sounds good. So we match Raina with Toyota. And the way we draw this matching out is we put the domain element first. It's the x coordinate. And then we put the y coordinate as the corresponding range element. The range element that domain element is being paired with by this rule. Sandra, I don't know if you can talk or chat or send me a text. Sandra, are you there that you can tell me the make of car that you last arrived in? So Sandra, what's the last time? Okay, so Sandra, finally, she's at work and so she can't talk. But she did manage to tell me that she had arrived on campus in a Honda. Now, Sandra, by the way, you said a Honda Civic. We don't care about the Civic part of it. right? We just talk about the make of car here by this rule. So we'd say Soundra is the domain element. She gets paired with Honda. Shrell, are you there? All right, so Sherelle, we're going to make something up for you too, and we're going to say Toyota for you also. And let's see, I'll go ahead and put myself in here. I'll put the last time I arrived on campus, I was in a Subaru. All right, so we keep on going. We would list everybody in class, right? So those of you who are watching this recorded, right now, you should be sitting there, if you're watching this, and you should be saying to yourself, okay, what did I get paired with, right? So now the question is this relationship, because it's certainly a relation, because it's any pairing of the domains with ranges. So it's certainly a relation, but in particular, is this a function? Does every domain get assigned to one range? Now, what you have to be careful about here, and what will bother people sometimes is, so for example, I've got Raina being matched with Toyota and Shrell being matched with Toyota also. And so that, that's kind of worrisome. Does that violate the definition for the function? So remember, the definition says every domain gets assigned exactly one range. Remember, those are the two things. Every domain must be assigned to exactly one range. And so we would just go through the entire class and we'd see if anybody did not get paired up with something. So in other words, somebody walked to campus, rode a bicycle to campus. So as long as everybody arrived in a vehicle, then we would be okay there. And so then this exactly one range. Well, the deal here is that all of you have been, if you arrived in a car, you only arrived in one car. There's no way you arrived in two cars, right? And that's not possible physically. It'd be crazy if it was, right? And so everyone is assigned to exactly one range also. And so this rule does satisfy the definition for a function. This is a function. Every domain gets assigned to something, and it gets assigned to exactly one thing. Now notice this Raina Toyota and Shrell Toyota business there. What that implies there is they have the same Y value, the same range value, and that's okay. That doesn't violate the definition for a function, because Raina gets assigned to just one domain, Shrell gets assigned to just one domain. They happen to be assigned to the same domain, but that doesn't matter as far as the definition goes. So we go back to the definition, and we are going to write down underneath here that repeated Y values, in other words, ranges, are okay, right? When you have a function, it's not a problem if you had repeated Y values. That's not a big deal. All right, so now that was rule 1, notice, so that implies there's going to be a rule 2. So we have the same domain and range, same domain and range, but now we have rule 2. And rule 2 is everyone in class, everyone is assigned the make of car they own. All right, so that's different. So now, when you talk about the make of car you own, then ownership means, and so all of you need to be sitting down thinking, okay, what am I assigned to by this definition, this rule? Ownership means your name is on the title, right? There can be a lien holder on there also, but if your name ain't on the title, you're not the owner. So some of you may be, it's possible you don't own cars. Remember, a domain a function has to assign every domain to something. So in this case, any of you, and I'm sure there are several, any of you that do not own cars will be thrown out of the domain. So what we do, if we have domain elements, and this, by the way, is exactly what we're going to do in more mathematical functions here. Any domain that's not assigned to something by the rule that you're talking about, you actually throw it out of the domain. So we take all you non-car owners and we throw you out. And by the way, another example of that, a more mathematical example, might be something like this. If you have y equals 1 over x minus 2. If that is the rule for a function, right, that equation tells you how to take an x value and assign it to a y value. So like when x is 3, right, you get that y is equal to 1 over 3 minus 2, or y is equal to 1 over 1, or 1. And so when x is 3, y is 1 with this rule, right? This rule assigns the x value, the domain value 3, to the range value 1. When x is negative 4, I'm just picking 3 and negative 4. These are just values picked out of thin air. You just put negative 4 in place of x, and you get 1 over negative 6. And so this rule takes the domain element negative 4 and assigns it to the range element negative 1/6. However, notice when you pick x equals 2 here, you get y equals 1 over 2 minus 2, or y equals 1 over 0, and that is undefined, right? You can't divide by 0. And so notice that 2 does not get assigned anything. So what do we do here? We throw, so 2 is not assigned to a y value, so it is thrown out of the domain. Right, so the domain on this particular equation is every x value except for 2. Right, 2 does not get assigned anything by this rule. All right, so that's a somewhat more mathematical example, but it's the same thing. So all going back to our rule now at the top, all people who do not own cars get thrown out of the domain. And so then we start looking at this exactly one part, right? Exactly one. So each domain assigned to exactly one range. So is that true for this particular rule? Well, let me write down here that since I'm in the domain, right, I'm going to put myself as the domain element here. And when we're talking about car ownership, I own a Subaru, but I also own a Toyota. And so what have you got there? You've got one domain element. Those are two ordered pairs, but it's the same domain element. One domain assigned to two ranges. And that is a problem, right? That can't happen if you have a function. And so notice that now what do I have? I have repeated x's, repeated domains. Right, here's repeated x's. And that's an issue. When you have a repeated x, then that means you have an x value that's assigned to more than one range value. And so going back to my definition, I add another statement at the bottom here that repeated x values, in other words, domains, are distinctly not okay. Right? And if you have a repeated x value, that means you do not have a function. You have a relation, but you don't have a function. Okay, so now we're starting to get somewhat of an idea of how this works out. So now let's look at maybe what you might call a little bit more mathematical type of examples, possibly. Let's just look at some sets of ordered pairs and see if these sets of ordered pairs would match the definition, or would satisfy the definition for a function. So let's say I have a set of ordered pairs that's 0, 1, 1, 2, 2, 3, 3, negative 1, 4, negative 2, and 5, 2. I have 6 ordered pairs there, and I want to see if this particular set of ordered pairs satisfies the definition for a function. So let's see. First of all, let's name this set of ordered pairs, and I'll name it with a small letter f. Small letters F, G, and H are the most common letters to use to name a function. All right, so the domain of F, the notation is that we put a capital D for domain, and we put a subscript of F. And this is the domain for this set. And you just list out the domain values. 0, 1, 2, 3, 4, 5. By the way, domain elements also go by the name input values. So inputs, they also, you talk about the domains as being the independent variable. Right, so the domains are the x values, the input values, the independent variable. The range of f, the notation there is a capital R with a subscript of f. And you just write out the y values here and list those. So 1, 2, 3, negative 1, negative 2. And I wouldn't put 2 a second time there because we're just making a list here. Ranges are sometimes called the outputs or the dependent variable. All right, so is this particular set a function? Is f a function? And the deal is every domain is certainly assigned to something, and every domain is assigned to one thing. In other words, there's no repeated x's. That's all you have to look at here, is no repeated x's. And so this is a function. So f is a function. There are repeated y's, but that's okay. All right, some notation here that we want to look at. This is called function notation. And since f is a function, we can use function notation here. And with function notation, we would say that f of 0 is 1. I mean, that's because of the point 0, 1, right? The x value is 0, and the corresponding y value is 1. So we actually write that the function f takes 0 and it assigns it, or it matches it up with 1. F of 1 is equal to 2, right? This function f takes the domain value 1 and it matches it up with the range value of 2. F of 2 is equal to 3. F of 3 is equal to negative 1. F of 4 is equal to negative 2, and so on. Right? This is called function notation. All right, if you look at the graph of this function, you could, even though there's just a bunch of dots, you could look at the graph of this function. And the graph of this function, let's see, we got the point 0, 1, we have the point 1, 2, the point 2, 3, 3, negative 1, 4, negative 2, and 5, 2. That's the graph of our function right there. And the graph of this function is just a bunch of dots, right? Don't connect the dots, because then you're talking about more than just this set of ordered pairs. And so that's the graph of this function. There's nothing wrong with a graph to look like that. All right, let's look at another set of ordered pairs. So the next set of ordered pairs looks like this. Let's say we have 0, 1. Let's back up on there. Let's say 0, 3, 1, 3, 2, 3, 4, 3, 5, 3, and 6, 3. That's our set of ordered pairs. Now notice this relationship here, that every domain value is actually assigned to the same range value of 3. We could name this set G, and then the domain of G is 0, 1, 2, 4, 5, and 6. 0, 1, 2, 4, 5, and 6. And the range of G, there's only one element in the range, and that's just 3. Like that. Is every domain assigned to exactly one range? Absolutely. Are there any repeated x values? No, there's not. And so this is a function, right? There's no repeated x's. And so this is a function, even though every range is the same. That's okay. There's nothing wrong with that at all. And so the graph on this particular function will look like this set of dots. 0, 3, 1, 3, 2, 3, 4, 3, 5, 3, and 6, 3. That's our graph right there. Just again, a bunch of dots there for this function. All right, let's see. Another set. Let's say this is H. That's the name of this set. And H consists of these ordered pairs: 0, 1, 1, 2, 1, negative 2, 2, 4, and 2, negative 4. That set of ordered pairs. All right, so the domain on this set H, the set of x values, would be 0, 1, and 2. Remember, we don't write things down if they're repeated. And the range on H would be the values 1 and 2 and negative 2 and 4 and negative 4. And then the question, is this a function? Yeah, there are repeated x's here. There are repeated x values. And so this is not a function. It is a relation, but it is not a function. If you look at a graph, let's see, so you have 0, 1 right here, and then you have 1, 2, and then you have 1, negative 2, and then you have 2, 4, and then you have 2, negative 4, way down at the bottom there, like that. And so this is something that is not a function, right? And does not represent a function, this relationship. Now I do want you to notice that when you have repeated x's, and remember, repeated x's means you don't have a function, right? Because there are repeated x values here. But when you get repeated x values, notice those repeated x values always lie on the same vertical line. So 1 was a repeated x value and 2 was a repeated x value. And when you plot those points, you get the same vertical line. So repeated x's always fall on a vertical line, on the same vertical line. So let me put the word same in there. All right, and so that actually is a nice, something that's good to observe here, because that actually allows you to be able to take any old graph and decide whether it represents a function or not. So if we look at this particular graph, even though it's not a set of dots like I've been talking about, I can still look at this graph and decide whether it represents a function or not. So let's say I've got these dots right here, but now not just those dots, but I actually have a curve that connects those dots, and this is my relationship right here. And let's say that the curve actually just stops at those values right there, like that. No arrows there. So notice that there's no way, wherever you draw a vertical line, the vertical line only crosses through the graph one time. And so there are no repeated x values here. No repeated x values. By the way, how many points are on this graph? There's another question I would ask here. And don't tell me that there's 5 points on this graph. There's an infinite number of points on this graph. There's an infinite. Anytime you draw a curve like this, you automatically get an infinite number of points. Now, I've only got 5 points plotted. 5 points are plotted, but there's an infinite number of points on the graph. All right, and when you have no repeated x values, when all the vertical lines only cross the graph once, we say that this graph passes what we call the vertical line test. And now I usually abbreviate the vertical line test to just VLT for vertical line test. And that means that every vertical line I draw on this graph only crosses it once. And so a graph that passes the vertical line test, the graph is a function. The graph is a function. All right? So now if you look at this graph, all right, so let's say that this graph goes through these points, like so. Now this graph right here, also an infinite set of points, but notice the difference here is that you do get, if you draw vertical lines here, notice you do get repeated x values because of those vertical lines. So there are repeated x values here. And so this graph is not a function. And it is a relation, by the way, but it's not a function. And we say that this graph fails the vertical line test, because you can draw vertical lines that intersect it in more than one place. So it fails the vertical line test like that. Now in either case, let's see, so in either case you could talk about the domain and the range. And so I do want to talk a little bit about that also before we close this up for the day. I think we wanted to get as far as we could into functions. That will set us up good. There's a certain amount of material I have to cover before exam 3. And the fact that we've got as far as we have into this stuff with functions just means that will be less we have to cover on Thursday of this week and Tuesday of next week. So that's a good thing. We can get this stuff taken care of and hopefully address all of your concerns here. So let's finish this day talking about a little bit about function notation, and then that will be all we're going to talk about for today. So we're going to do a little bit with function notation here, and then we are going to shut it down for the day. So we've talked about the vertical line test. We've talked about the definition for a function. And so now we want to talk about function notation a little bit more carefully. So when you have an equation that represents a function, so let's say we have y equals 2x minus 3, just some old equation, in this case a linear equation. You could certainly look at the graph of this. You know that the graph is a line, so this is a function, right? The graph is a line, and it's a line that has a slope of 2, so it's a slant line, so the graph is a function. It passes the vertical line test. Graph is a function, passes the vertical line test. All right, now when you have an equation that represents a function, frequently what you do is instead of writing it as y equals 2x minus 3, you write it as f of x equals 2x minus 3, or g of x or h of x, right? You use a letter to name the function. Now notice what I'm doing here is when you use function notation, in place of y, you're writing f of x. Y and f of x mean the same thing. So y and f of x are kind of interchangeable symbols. And so where you see a y, you could put the function notation f of x. Where you see f of x or g of x, you could replace it with y. That would be okay to do. This is common to do. One thing that's important is this allows you to name the function, but then this also allows you to do things like this, to find f of 2, for example. And f of 2 would simply say, take this function and wherever you see an x, put a 2. Right, so f of 2 would be 2 times 2 minus 3, or 4 minus 3, or 1. Right, so we have that f of 2 is equal to 1. So now remember that 2 is the x value and 1 is the y value. The 2 is the domain, and so this is always f of a domain equals a range, or f of an input value equals an output value. Right? Those all really are saying the same thing. And then finally, it also says that you've got the point 2, 1. Right? That when x is 2, y is 1. F of 5 for the same function then. This would be 2 times 5 minus 3. Right? Every place I see an x, I'd put a 5. And so that'd be 10 minus 3, or 7. And so the ordered pair would be 5, 7. Right? When the domain is 5, the corresponding range would be 7 for this particular function. F of negative 6 would be 2 times negative 6 minus 3, or negative 12 minus 3, or negative 15. So when x is negative 6, y would be negative 15, like that. All right, so certainly I would want you to be able to evaluate some basic function notation. Like if we have g of x is equal to x squared minus 2x minus 4. Just be careful with the arithmetic. G of 8, right? Every place I see an x, I would put an 8. So this would be 8 squared minus 2 times 8 minus 4. And you see, every place I have an x in the function, I'm replacing it with 8 here. So then you just do the arithmetic. This would be 64 minus 16 minus 4. So that would be 44. So g of 8 would be 44. That would give you the ordered pair 8, 44, right, on the graph. G of negative 5 would be negative 5 squared minus 2 times negative 5 minus 4. Just every place I see an x, I put a negative 5. Use parentheses anytime you're substituting in place of x like this. So this would be 25. G of negative 5 would be 25 plus 10 minus 4. G of negative 5 would be 31. And so the ordered pair here would be negative 5, 31. Now finally, you could do the same kind of thing that I just did right here with a graph. So instead of being given an equation, you can use function notation just on a graph as well. So let's say I have a graph, and this will be probably my last problem of the day here. Let's say I have a graph that looks like this. And let's go ahead and carry it over like that. Now this graph, let's call this graph F, and this passes the vertical line test. So this graph does represent a function. And so you could use function notation here. So for example, if I wrote f of 1, right? F of 1 in this graph, when x is 1, here's x equals 1, you go to the graph, and you get a y value of 4, right? And so f of 1 is equal to 4. Whoops, don't need parentheses there. F of 1 would be equal to 4. And that's because of this point, 1, 4 on the graph. If we looked at f of 6, we would go to the x value 6. Here's the x value 6 right here, and we go to the graph there at that point, and so you get f of 6 to be equal to negative 2. Because of the point right here at 6, negative 2. F of negative 1 would be, here's x equals negative 1, right there. And we go to the corresponding point on the graph, and that would be y equals 1 right there. And so f of negative 1 is equal to 1. And that's because of this point, negative 1, 1, like that. Finally, let's see, f of 4, that's this point right here, 0, 4, 0, right? So f of 4 is equal to 0. So I would expect you to be able to read function notation from a graph as well, like that. Not just from an equation, but from a graph. All right, so we will do more with this definitely next time, and we'll continue on our discussion of functions here. So you should definitely be looking at WebAssign homework and working on WebAssign homework. And let me just quickly point out here that, let's see, I guess that would be it. I don't need to point out anything else. So I'll be working on WebAssign homework. We'll be continuing on with functions next time. Have a great day.